So what we have done in the previous lecture, we have calculated the Feynman amplitude of certain diagrams. Okay. Now we will do a calculation using the Feynman rules and the Feynman diagrams. Okay. So we'll be doing an explicit calculation of a decay rate. Okay. So the process what we are trying to study is a boson is decaying into a fermion and antifermion. A scalar boson is decaying into a fermion and antifermion pair. Clear? So let's try to calculate at what rate it decays. Okay? If I know the decay rate, I can know the lifetime, because the decay rate is inversely lifetime of a particle is inversely proportional to the decay rate. Okay? Rate means 1 by time simply. Okay? If I have to calculate the lifetime, that means you have to invert the decay, this decay rate. Clear? Samajh? So if I calculate now the decay rate, I will be able to figure out what is the lifetime of a particle. Let's say if you are having a Higgs particle that decays into fermion and antifermion pair, so you know its decay rate, let's say up to the lowest order of the perturbation theory, so you will be able to know what is the lifetime of that particle. Clear? Let's say if you are any other scalar boson, it decays, or let's think of a mu1. I will not be doing a calculation of mu1 here. Okay, that you can do. Let's say you are having a mu1 that decays, okay, into other particles, okay, through, let's say, this weak interaction. If you know the decay rate, you can calculate the lifetime of the mu1. Okay, for that matter, let's do some calculation first. Okay, so last time what we have done, so this scattering matrix elements we have written like this. Okay, delta Fi. I is the initial state and F is the final state. A particle starting from the initial state to the final state. So these are the matrix elements. Clear? So then you are having here a particle same initial state and the final state. That means it does not interact at all. So the delta Fi term. Then you are having this kind of thing. 2 pi raised power 4 delta 4. Overall conservation of the total momentum. Okay, I means initial, P means F means final. Okay, so this was our overall conservation. Then what kind of product factors we had? Then you are having for each initial state we had this kind of factor twice I EB. For each final state we are having this kind of factor, and then okay, so these are all the kinematical factors. Then we are having the Feynman amplitude. Okay. So this is the process. Okay, so what we will do, we will consider only one particle. Okay, decay. Let's think of only one particle. Okay, so you are having one particle. Let's say your phi is going to some this fermion plus antifermion. So we will consider this kind of process. So your boson goes into fermion antifermion pair. So that means in the initial state, okay, so the initial and the final states are different, clear? So it means this delta does not contribute. So if I need to calculate what is the scattering matrix element, so I need to ignore this thing. So you got it? Okay. So then I can remove this thing. So I can write this scattering matrix element SFI as like this thing. So because our initial and final states are different, okay? So that delta does not contribute. Okay, now let's calculate the transition amplitude. So I know the scattering matrix element. What is the transition amplitude? Such that the particle makes transition from state I to state F. So it will be simply, so I can write now the transition, transition probability. Okay, so this scattering matrix element represents transition amplitude, okay? So it is actually proportional to this Feynman amplitude. So I can write the transition probability such that the particle goes from the initial state I to the final state F. Okay. So what is the initial state here? Phi, and the final state is actually fermion antifermion pair. So I need to take the mod of this as Fi square. So this is our transition probability. Clear? So if this is the amplitude, its mod square will give me the transition probability. Clear? Okay. So now if I take the mod square of this thing, so I have to take mod of this thing, mod of Fi square. So that means transition probability is proportional, or the mod square of the Feynman amplitude gives us a transition probability, clear? Because it will be simply proportional to this thing. Okay, and including you can have these factors as well. Okay, now the point you can square this thing. Sorry, so it is ruled. So it is ruled. It's not on it, it's a root factor, right? Okay. So then you have to also square this delta function. Okay, when I take the square of this thing, okay, square of this s, what I have to do? I have to take square of the delta function. Okay, so what does that mean? So it means like this. You are having delta 4 of x, let's say for the time being. Square means, so let me write p because the argument is p. So it means like this thing, delta 4 of p. Okay, so this is a square. Huh? I need to take the product. Okay, so if I take now this objective, so I can take one delta function to be what? As a delta function, another let's consider as a function. Okay, so what it gives me? Okay, so you can write it as a delta 4p, okay, whole square. This 4 means it's actually a 4-dimensional delta function, right? It's not the power, right? Okay, this is power, this square, right? So what it means? It means I will get delta 4p, okay, and then delta 4 of z. And now, okay, so this is in the momentum space. Now I am having this a divergent quantity. So this I have to fix. So once I take the square of this delta function, I will encounter this delta function. A delta function evaluated at this 0. So this is actually I mean what it is. It's a divergent quantity. So what I will do? We'll go back to the box normalization as well now, and let's put, okay, so I am having particles within the box of volume V. Okay, let's consider that at the end of our calculation we can take this V tends to infinity. Clear? So you got it? Okay, so what I will do, okay, okay, so what I am having here, okay, so what we will do, we will consider a box of volume V, box of special volume V, okay? So now what is our this delta 4? Let's write this delta 4 of P. So it is actually a 4-dimensional delta function. So I need to integrate over 4 volume d4 of x. Clear? And what will be in the denominator? 2 pi raised for 4 e raised for minus I p dot x. So these are 4-dimensional variables. Okay? So this I can write in this very fashion. Limit of, so let's write this 4-dimensional volume to be omega. So let's take omega. So it is omega. It will be something d4 of x. So now I have considered. Okay. So omega is what? It's a 4. Okay? It's a 4-dimensional volume element of the volume. Clear? So V is the special value. So now let's take, therefore, so I can write this delta 4 of 0. So what I will get? So it is limit of omega tends to infinity. Okay? So let's put P here. It means it is in the momentum space. So it is simply integration over this d4 of x 2 pi raised for 4. Okay? So that will be simply limit of omega tends to infinity. I will write this as omega because this is integration over 4 volume. It will be simply omega. So it is 2 pi raised for. Okay? So what is omega? It's a 4-dimensional volume, and I am considering V to be the special volume. Okay? So that means I need to multiply it by the another dimension. That is the time dimension. Since we are working with c equal to 1, so I will multiply it by t here. The hyperline or the hypersurface t here. So this I can write symbolically to be. Okay, since, okay, wait a second. So we will now use this delta 4p in the box to be what? Omega by 2 pi raised for 4. So in our box, we will use, okay, we use this delta 4p0 as omega by 2 pi raised for 4. At the end of the calculations, we will put this omega tends to infinity. Okay, so this I can write as the special value multiplied by the t is, think of the time dimension. Okay, it is c times t. Okay, it will give us the extension in the time coordinate. Okay, so divide by 2 pi raised 4. Okay, okay, so therefore I can write this delta 4 p. Okay, it is squared, therefore I can write it as simply, okay, delta 4 p, okay, delta 4 of 0. So what this object is? So it is simply Vt by 2 pi raised for 4 delta 4. So this is our square of the delta function, but where? In the finite volume omega. समझ आवा? If I take omega tends to infinity, it diverges. तो ये बात समझ? Okay. At the end of the calculus, when we put omega tends to infinity or this v tends to infinity, we will see all these v's cancel. Okay? समझ आवा? Okay. So now let's go to let's go to our this mod of SFI square. So what it gives me? We are considering initially one particle. Clear? Okay, so let me write it first. So it is 2 pi raised for 4 delta 4. So I will consider pi. Sorry, let me take p to be the initial momentum. How many final moment? Okay, let me write k. What? Okay, for the time being, let's write it. Let's write pi. Pi to be the initial momentum, and so it will be final momentum. We are having 2. Okay, I am considering only that process. So if I consider, let's say, initially you are having many particles, and finally you are having many particles, just put summation here. Summation I means the initial state, initial momentum. Okay, then what I am having here? Product of I. So I will not be having now the product. I will be having simply one factor, root of twice v ei. Ei is the energy of the initial particle. Then I am having this product over here, 1 divided by root of twice v ei. For each final particle, you will be having this kind of factor. Okay. Then okay. So I need to take the square, and I will be having mod of n, because mod of I is 1. Okay. So what you get? So 2 pi raised for 8. And what you will get from here? Can anyone tell me? Now it is the square. Okay, what is the square of the delta function? So it is Vt by 2 pi raised for 4. Then delta 4. What is the argument? Pi minus summation of f. Clear? Now let's take the square of this thing. So it is 1 divided by twice v. Okay. What is the square of this thing? So root will go twice v. Okay, then you are having mod of m. Clear? Okay, so what you get? So let's divide by, okay, so let's write it. So let me write transition probability per unit time. Okay, what does that give? Transition probability per unit time. That is your decay rate. Clear? Is it true? Huh? So if you take transition probability per unit time of a particle moving from initial state I to the final state F, what that will give me? A decay rate. Simply? Okay, so what that will give me? So that is simply equal to this mod of SFI square divided by this t. Okay? Someone now tell me what we get from here. So that is equal to 2 pi raised for 4. Okay, so this v and this v cancels out. This 2 pi, okay, so this I have already cancelled. So you are having this delta 4 pi minus summation of f pf. Then what you have? 1 divided by twice ti. Okay, then you are having product 1 divided by twice v f mod of Okay, so this actually gives us the transition probability when you go from one discrete level to the another discrete level. Why discrete here? Can you tell me? Because we have considered a box of volume, a finite box. When you confine your particle within the box, what will happen to the energy levels? So they will turn out to be the discrete. Okay, so that means you are going from a particular initial state I to a particular final state F. Samajh? So in that case, if you know what is the particular initial state, what is the particular final state, then this okay. You substitute for the values of this MFI. Okay, so this will give you the decay rate. Clear? But we will not be interested in, since now we can extend our volume to infinity. Clear? Samajh? So that means I will put my detector at the infinity. What will happen? So the nature of the energy states will be continuum. Or in other words, my momentum states will form a continuum of the states. Okay, I need to look what is the probability for an initial state going, okay, from, let's say, from particular state to a continuum of the states. Okay, so those continuum of the states are actually our momentum eigenstates here. Okay, because after the interaction has taken place, the particles are essentially free. Okay, when you are having particles free, it means their eigenstates are, they are the momentum eigenstates. Okay, so much on. Okay, so what I will do, I will look at, okay, so of the transition probability, this decay rate into a volume. Let's say, suppose you are having a detector, okay, or okay, so you collect your particles here, okay, so they will go into, let's say, these kind of states. Okay, so let's say you are having the volume. So let's consider the volume D3P. Okay, within this finite infinitesimal volume, let's look at what is the probability or the transition probability per unit time such that the particles are, captured within this very volume element, or they make a transition from the initial state I to the final states, okay, which form a continuum, okay, and we'll look at this small volume element. Then we can integrate out this entire volume. So in other words, okay, so let me put it like this thing. You are having some initial state I, so it makes a transition to all the, so this is a continuum of the final states. Okay, so in this very volume element, you look for first the volume element D3P. Clear? Okay, then you integrate over all the possible final states. Samajh? How I can calculate, okay, the number of states within this very volume element? Because this small volume element will be having a certain number of states. Clear? I have to calculate what are the number of states within that very volume element. Okay, so that means a particle makes a transition to that set of states. And that set of states actually continuum. How I can do? I need to figure out what is the density of the states. Is it? How many possible available states are there in a volume V? Okay, if I know in a given volume how many possible states are, then I can multiply. I can figure out what are the possible states in this D3P. How I can do that? So you do it like this thing. Okay, so let's say you are having a phase space. You divide it into cells of volume how much? So 2 pi h cross q. Okay, so let's take you are having a phase space. Okay, so let me draw it. So you divide it into cells. Okay, because we are in the momentum space, that means the phase space is relevant. Okay, so you divide it into the cells of how much volume? H cube. So this is actually h cube. Okay, so let's say you are having a 2 pi h cross q is the minimum volume what we can have. Okay, in that very volume you put one particle. Okay, each phase cell then contains how many particles? One particle. So that means you are having these number of particles per unit volume. So much. So now if you are having this phase space of volume V, so this will be the amount of particles or the number of states, because you are having one particle in each cell. Okay, so much. In other words, you can have this number of states in the volume V. Clear? So much. So this will give the density of the states within the volume V. Okay, so it is a phase space for the free particles. So much. Okay, so now in a volume D3P, you just multiply it D3P. So these are the number of available states within the volume D3P. Clear? So this is how we do it. Okay, so now what I will do, I will take this SFI square by T, multiply it by that very factor. Clear? समझ आवा? And integrate over the entire volume. Now look here, this very factor. So you are having this D3P. How many particles I am considering in the final state? 2 particles. So that means you will be having 2 volume elements for 2 particles. समझ आवा? Is it correct or not? Because you can receive one particle in one detector and another particle in the another detector. So that means how many factors of D3P will be? 2. So that, in other words, for each particle you will be having this kind of factor. So let me write for symbolically. Okay. Okay. So let me write decay rate. Okay. So let me write this gamma as a decay rate. So what I will do, I will integrate it over. So this is simply symbolic. Okay. So this V by 2 pi h cross q, okay, d3p, okay, then you are having mod of sfi square by dt. Clear? So Muzaffar, everybody got it? Okay. So now let's try it for our process. Okay, so our process is you are having this boson goes into fermion plus anti-fermion. Okay. So therefore I can write the decay rate for this kind of process. Now tell me what I will do. So this is an element for each final particle. Huh? So this is for final particles. Huh? Clear? So समझ आओ? So that means I am integrating over the final states, all the possible final states. So what it will be? It will be V by 2 pi h cross q, okay, d3p. Let's write it for the final particles. F means final. How many final particles I am having? 2 final particles. So let me put a product. समझ आओ? Okay. So then, what is this very factor? 2 pi raised power 4. Okay. Then you are having this delta 4. So pi minus summation over f pf. Okay. 1 divided by twice ei. Ei is the initial energy. Then product f twice ef. So mod of. Is it clear till this point? Everybody followed it? So if you know, okay, if you are able to, understand this kind of formula, then it will be easier to do a simple calculation. Okay? So, okay, now look here. This EI does not depend on any final momentum, is it? Integration is only over which momentum? Final momentum. So you can take this very out. Twice EI, yeah? Okay. So now look here. So you are having 2 pi raised power 4 here. So let me take only 1 divided by twice EI. Only this thing, this data. Okay. Then I will write it this way. Integral. Okay. Now look here. So each final factor is carrying this V, is it? Samashama? And each final factor is carrying 1 by V. So this V and V cancels out. Clear? So then you are having each final factor carries this 2 pi h cross q. And you are having each factor containing what? Twice EF. So I will club them together. So I will write it like this thing. D3PF. So V cancels. So it will be simply twice V. Okay. Let me write 2 into 2. Sorry, E. Okay? समझ आओ? Okay? So then what you are having? Huh? Oh yes, 2 pi h cross. Then you are having this 2 pi raised power 4 delta 4 pi minus summation of f ef. Okay? Then you are having what? Mod of m square. So this will depend on the final momentum. This mod of So I need to now evaluate this very integral. Clear? So now let's go to the process. Okay, the process what we are looking at. No, we have not done any kind of explicit calculation. Okay, we'll do it in the lowest order of perturbation theory. Any question? So let's consider this process. So you are having a decay of a scalar boson into fermion antifermion. Okay, so what I mean by that, so I'm having this kind of process. So let me write K as B as the quanta for the, or B is the symbol for the scalar boson, K means the core momentum vector, so it goes like this. So let me write fermion as the electron, so it goes into this momentum state P and S, and the positron means the antifermion. Okay, so the lowest order diagram is what? So let's take lowest order diagram. So this we have already done. So I am taking the lowest order. Okay. So this process happens through the Yukawa interaction. So G minus G probably psi bar psi. Okay. So I am considering this process to happen through Yukawa interaction. So the lowest order diagram is like this. Okay. So this is your P of K, and this is E minus Ps. Clear? Okay, so now let's write. So in order to calculate this decay rate, what I need to know? Feynman amplitude. Only the unknown quantity is what? In that term, the Feynman amplitude. Now let's write the Feynman amplitude of this very process. Now tell me, what should I write? What is the coupling constant? G. Is it? So this will be Ig. Okay? So this is your Ig. So now what I will write? So for the final particles, because there is no propagator at all, I need to consider only for the final particles. For the fermion, it is U bar Sp. Clear? So momentum is P and S. So Ps is the spin, and for the fermion, antifermion, it's Ps plus. So this is our what? Feynman amplitude. Okay. So now let's plug in the formula. I need to calculate mod of what? Okay. So therefore, so mod, so it will be like this. So it will be simply G square. Okay. Mod of U over Sp. Okay. Vs prime. Okay. So now if I use this mod f square in that very integral, and I can integrate over. Okay. So let's pause a little bit. So it means the this boson has decayed into this electron and positron pair. You can detect this electron or the positron or this fermion and antifermion in the spin state S. S can take two values. It can be either in the up spin state or in the down spin state. You can think the antifermion as well in the same way. Okay. So in other words, when you, let's think, if I consider in a particular spin state, let's say your boson is decaying into this electron and positron. Okay, if I consider now my electrons in a particular spin state, I want to detect it in, let's say, in the up spin state, okay, or in the down spin state, or whatsoever, any kind of possibilities. Then this is okay. So you can plug in the values of what? What is the formula for, okay, you know, for the Dirac fermions, U is what? That column vector, okay, and for E spin you are having. So we have written the solution of Dirac equation, because these are the what? The solution of the Dirac equations, this U and V, is it? And I know what are the solutions. Then you just plug it in the integral, you get the values. So it is all, if you consider the particular spin state. But I don't want to consider a particular spin state. I want simply the particle goes into, you just detect an electron, not in a particular spin state. You detect a positron not in a particular spin state, okay, in an arbitrary spin state. Or in other words, you don't care about the spin at all. समझ? You want an electron, it's the electron. Okay, whether it is in spin up state or spin down state, it doesn't matter. Okay, but let's not bother with the spin components. Clear? So what I will do then, I will simply take the average over the final spin states or sum over all the possible final states. If I sum over all the possible final states, what I will get? I will get actually the uniform probability throughout. Is it? So समझ, I will get actually the decay rate. It goes into the electron and the positron. So समझ, not in a particular spin state. Okay, so let's consider let's don't consider the spin here. Okay, and we average out the spin variables. Instead of averaging, I will not average. I will simply sum over all the possible spin states. So, so let's write then the decay rate in that case. Everybody got this very point? Huh? Okay. So let me write. Okay. So let's not be interested in the final spin states. Okay? Such that we sum over all possible spins. Final spins. समझ आवा? So therefore I can write this decay rate gamma is equal to 1 divided by twice EI. Clear? So integration over. So let me write this final. Yeah. Okay, T3PF divided by 2 into 2 pi h cross q. Okay. So since we have put actually h cross equal to 1. So we are in the, because all the formulas what we have considered where h cross is equal to 1, so I will not use this h cross. Right? So at the end of the calculation you can put h cross back. Right? So then what we are having here? EF. Okay? So you are having here a factor 2 pi raised for 4. Then you are having this delta 4. What is the initial momentum? That is K. Minus what is the final momentum? There are two, P and P. समझ आओ? Because sum over F, PF means P plus P prime. Okay? Because there was a minus sign in front. That's why you this thing. Then you are having summation over S and S prime. What are the possible spin states? You are having S and S prime. Is it? So that means you sum over S and S. So you get this G square I will put here. Because it is okay. U bar SP V S prime. Okay? Is this point clear? Okay, so what I need to first evaluate is, okay, so I need to integrate this thing. Before doing an integration, let me evaluate this very sum. Okay, so when you get such kind of integrals, including a sum over spin, there is a step-by-step procedure to be followed. First, you evaluate a spin sum. Okay, once you evaluate the spin sum, then the all formulas become simpler. Okay, then you integrate. Okay, so let's evaluate this spin sum. Okay, so I will evaluate a general kind of spin sum here. Okay, so then, okay, if you look here, so what you are having U bar, it carries a momentum P and spin S, is it? You are having a V, it carries spin S prime and P prime. Since this is a mod square, so it means this factor multiplied by its conjugate. So it means you will be having U bar and U, V and V bar. Clear? Okay, so there are the formulas what we have derived already. Okay, so these kind of formulas. Suppose if I am having summation over S, this U S P, okay, U bar S P, like this thing, U bar, it's something P slash plus N. Okay, and if I am having summation over S, V S P, okay, V bar S P, so it is equal to what? P slash minus. समझ आवा? The other way around. So this needs to be checked. Yeah? So this is it. Yes, it's correct. Yeah? समझ आवा? So these are the spin sums. So I want to utilize these formulas. Eh? So समझ आवा? So memorize those kind of formulas. Okay. So let's go to this very spin sum. So the first step is spin sum. So let's call this formula as 1. Okay. So I will define my spin sum sigma. Okay. समझ आवा? So let me write it as summation of S prime mod of U bar. Okay. So from here so let me introduce a factor F here. So I will take a general one. Then it will be easier to work that out. Because this will be used later on as well. This kind of formula. So then you are having this V S prime P prime. I will tell you what this F is. Okay. So F is a 4 by 4 matrix, arbitrary 4 by 4 matrix. Okay, because your Sepners are 4 columns, is it? It's a 4 column. U and V are 4 column vector. That's why F has to be what? A 4 cross 4. So it's an arbitrary matrix. It is neither Hermitian whatsoever. It's some arbitrary matrix. I will keep it there. Okay. So let's write that. So I will write it as like this in summation over S prime. So let's take, so it is U bar SP. So take this F, okay. So now let's multiply it by the conjugate. So you are having this direct term, and now mod square means its conjugate. So what it means? So you write this U bar SP, okay, F, V S prime, P prime, okay, then take the conjugate. Clear? समझ आओ? Okay. So now let's write it S prime. So it is U bar S P, okay, F V S prime P prime. Okay. So what this means? What this conjugate means? So it means the dagger of this thing. So V dagger S prime P prime. Then the dagger of F. Clear? Then the dagger of what? U bar. What is U bar actually? This U bar is actually U dagger gamma naught. Clear? So I will write it this way. So it is this thing U dagger SP, okay, and then you are having this gamma naught, its dagger. So this U bar is just for you, your purpose. I have put this thing. Samushima, and I am having this. Okay, these are the identities. Gamma square is equal to identity, okay, and gamma 0 dagger is equal to gamma 0. Gamma 0 is always Hermitian, but the other gamma i's, they are anti-Hermitian. Okay, everybody followed till this point? Okay. So this I can write as, okay, so let me write it here. So this sigma is then equal to summation over S prime. So you are having U bar SP, okay, F V S prime P prime, okay. So now what I will be having? Okay, now look here. Here you are having a V dagger, okay. This is a V dagger. I want to make it as a V bar. So that means I need to multiply it by what? Gamma naught. Samushema. So I will multiply it by gamma naught and use this very identity like this. So you are having this V dagger S prime P prime, okay. Use gamma naught. Clear? So gamma naught square is what? Identity. It doesn't matter. Now then you are having this F dagger. What you are having here? This gamma naught dagger will come this way. Okay, then you are having simply US. Our samajh? Okay. So this gamma naught dagger is what? Simple gamma. Okay. So I will use this very factor. So let's define this as F double dagger. Okay. So what I mean by that? F double dagger is something gamma naught F dagger. Okay, so let me use this thing. Everybody followed it? Okay, so what you are having? So this very object is simply V bar S prime. Okay? Clear? So this is equal to summation over S, S prime. So you are having U bar S P, okay, F, V S prime, P prime. Okay, so let me write it this way. Then you are having V bar S prime, P prime, F double dagger, okay, U S P. समझ आओ? Okay. Now, can anyone tell me about these things? So, what is the dimension of this thing? So, to simplify things, what is the dimension of this thing? This is a matrix, is it? This is a 4 by 4 matrix, clear? Now, tell me, V is a column vector. It's 4 cross 1. Okay, if you see, this is actually a 4 cross 1 matrix, is it? And this is what? 4 cross 4. What this is? 1 cross 4. Because it is actually the this row vector. So what is the total dimension of this thing? 1 cross 1. So it's a number, is it? It's simply a number. 1 cross 1 means a number. And this also what? A 1 cross 1. So what I will do, so if I look at this kind of pattern, I'll put simply the matrix indices. So these are the matrices in the Sittner space. So I will use those kind of indices like this thing. So let me write it as summation S, S prime, U bar S, let me write A, P, so F, A, B. Now look here, is this a matrix? Is this a matrix multiplication? Is this a matrix multiplication, everybody? It's a number, is it? You sure? Okay. So now this I can write V bar S prime, let's say C, P prime, F double dagger, let's say CD, U, S, P. समझ आवा? Huh? So these are simply numbers. Now if they are the numbers, okay, now I have put them in the explicit as a numbers. So matrix elements, I mean to say. So then I can displace each and everything. Because these are simply numbers, you can displace them. Okay, so I can write it like this thing, summation over S, okay, S prime. So let me take this objective, because this is U and this is U bar. Let me write it as USGP, if they carry the same momentum. And the condition is they should carry actually the same momentum. समझ आओ? This is very important because the formula what we have written, that U bar, they contain the same spin label and the same momentum. Then it is equal to P slash plus M. So समझ आओ? Okay. So let me keep this as such because I have nothing to do with this. So it is FAB. Then you are having V bar. Both carry the same momentum. Okay. So this is the momentum P prime. Then you are having V bar S prime C, P prime. Keep this as well. C. Clear? समझ आओ? Everybody got it? I simply displaced the variables to keep it in this fashion. Now let me write this thing. So it is summation over S. Okay, because this factor contains S, this contains S prime. You can take summation there. So it is USDP. Okay, U bar SAP. Clear? Okay, so this is one factor. Then you are having this F, A, B. Then you are having summation over S prime. Okay, V S prime P. Okay, P prime. Then you are having this V bar S prime C, P prime. Okay, so this factor, you are having this factor, and then you are having this F double dagger C. Okay, clear? So now what this is? So this object is what? Okay, so I can write it as, it is simply P slash plus M. Okay, what are the since this P slash is actually a matrix. Why? Because P slash is what? What is P slash? P slash is actually P mu gamma mu. Shall P slash means P mu gamma mu. So P is a variable and gamma mu is a matrix. It's a 4 by 4 matrix. So this is a 4 by 4 matrix. This M is not M. It's actually an identity here. It's a 4 by 4 matrix. Now tell me what this means. It is the this is the d8th element of the matrix. This U bar, is it? So I can put it like this in DE. समझ आओ? You can take this DA outside, put here. Then you are having u bar. Okay, u bar can write p slash plus m. Then what you are having? This f a p. This you can put as p slash prime minus m. So what are these things? B c. Then what you are having here? F double dagger c. Now look here. It's again a number. So this is dA. A and A is contracted, is it? Matrix multiplication, simple matrix multiplication. A and A. Then you are having B and B. Same. So what it means? It is actually DD element of this very objective. So in other words, it's actually a trace. Huh? It's a number. Huh? So much okay. Because there is a sum over these variables. So that means it is sum over D, sum over A, sum over B, sum over C. Clear? So much okay. So it gives me simply trace of what? P slash plus M F P prime slash minus M F double dagger. Now tell me, is trace a number? So what we had earlier, that was a number. Now it is again what? A number. Samushavan? It can be a function as well, but it's a number essentially. Okay. Now what is our actual form? So this is our sum. Huh? Samushavan? Okay. So what is our actual formula? Okay, actual formula is like this. Summation over S prime, okay, mod of U bar SP, okay, then you are in V S prime, P prime mod square, is it? Is this the actual formula? Now tell me what is sitting here. Here, there I had an F, is it? F is actually identity here, is it? So in this case, you are having, okay, so let me write. So F is actually identity matrix here. So when F is identity, what tell me? So F is 1. So this is identity, is it? Now tell me what about this F double dagger? That's again identity. Now let me write. F double dagger is actually gamma naught, F dagger, gamma naught. Clear? So this is what? Gamma naught identity multiplied by gamma naught. Because identity dagger is identity. What that is? Identity. Clear? So F double dagger is also what? Identity. So therefore this sum I can write equal to, okay, so this is equal to, so here in our case F is equal to identity. So it means it is simply equal to trace of P slash plus M, okay, and P prime slash minus. ठीक है? Okay. So now let's evaluate this very trace. This trace needs to be evaluated. Let's go. Then we'll plug in the formulas. Okay? Okay. So now let's go. Everybody has written this thing? Let's take this thing. So you are having this trace of P slash plus M, okay, and P prime slash minus. So what that is for? So I will write it as a trace. So multiply P slash P prime slash. It's like this thing. Then you are having plus P slash M minus P prime slash M. Then you are having plus, sorry, minus M square. Okay. Now tell me, this very factor contains how many gamma? 2 gammas, is it? So teacher, how many gammas this contain? 1 gamma. How many? This does not contain. What is the trace of gamma? Trace of odd number of gammas. Eh? That's equal to. So this formula I have already taught in the earlier semester. Okay. What is the trace of polyspin matrix? That is 0. Trace of gamma matrix is also 0. But if they are in, if you are having odd number of gammas here, let's say if you are having p gammas here, that's again 0. So if you are having, let's say, 5 gammas here, that is again 0. So it means, so which implies therefore this trace of p slash is equal to 0. That is same as what? Trace of p prime slash. Clear? So it means this does not contribute. Okay. So what it yields me? It's simply trace of p slash. I will write this p slash as p mu gamma mu. Then you are having p prime slash. Let me write it as a p prime nu gamma nu. Okay. समझ आओ, because mu and nu they are the main indices. Okay, so this is one factor. Then you are having minus m square. What this m carries? So there is an identity. So समझ आओ? So you are having an identity here. Everybody got it? So now let's take this p prime nu out. So what remains inside? So it is gamma nu minus 4 times m square, because this is a 4 by 4 matrix. So trace of an identity 4 by 4 matrix is 4. Huh? Oh, समझ आओ? Now tell me, now look at this very thing. So if I interchange mu and nu here in this very factor, forget this factor. So it is the same thing, because p's are variables. I can write it as p nu, p prime nu. Can I write it? So that means this very object is what? Symmetric under exchange of what? Mu and nu. So it means this product must be what? Symmetric under exchange of mu and nu. So समझ आओ? So I will symmetrize it. Okay, so you can symmetrize this thing. So you can write it as like this thing, trace over gamma nu. So this is the symmetrization rule. In other words, you can see like this thing. So interchange p mu and p prime nu. So it is one and the same thing. So that means the exchange of mu and nu here. This is symmetric in that. So this has to be symmetric. समझ आओ? Now tell me, what is this gamma? It is the anti-commutator of the gamma matrices. It is twice g mu nu. So this is equal to p mu, p prime nu. This 1 by 2 I will take out. So you will have trace of twice g mu nu and identity. Because g mu nu is a matrix in Minkowski space. Okay? So it's not in a, this trace is actually in the simpler space. If you see, it is trace over gammas. समझ आओ? Because trace, I have put actually the indices, the simpler indices. When I made this trace, I mean that that sum as a trace. If you look at this very sum, I have put this in the trace, but I have put those indices. They were actually different than this mu and nu. Clear? So समझ आओ? So those indices were actually in the simpler space. That's why you have to put an identity here. Okay? So minus 4 m square. This is very important. Be careful. G mu nu is a matrix in the Minkowski space. It has the elements in the Minkowski space. Because these are the Minkowski space, are the space-time variables. Mu goes from 0 to 3 and nu goes to 0 to 3. I mean space-time coordinates. So you take this out. Okay. So let's take this out. This 2 and 2 cancels out. You are having p mu, p prime nu, g mu nu. Okay, what is the trace of this identity? Multiplied by 4. Okay, so you take this out. What is the trace of this identity? 4 minus 4m square. So you can write it like this thing. So you take 4 out. So it is p mu. So this nu you can raise this nu up with the help of this thing. It will be p prime mu minus m square. So that is it essentially like this thing. So this is p dot p prime minus m square. Okay. So this is the value of the trace. समझ आओ? So let's proceed. Everybody got it? So you have to be very much careful using this very identity. When you are having this gamma nu plus gamma mu, or this anti-commutator that we write like this thing, gamma mu. So this actually equal to twice g mu nu. Okay, and an identity. Because gammas are themselves defined in the simpler space, but the indices and mu are what? Mu nu are in the coordinate space, are in the Minkowski space. That's why you put an identity factor here explicitly, so as to remember this identity is in the simpler space and g is in the Minkowski space. समझ आओ? So always use that kind of formula. That's very important. Okay, and this trace what we have done here, it is in the simpler space. It corresponds to that identity, not on the G. समझ आओ? So now let's go use this in the formula of 1. Okay, using in equation 1. So what is that? 1 divided by twice p pi integration over f d3 ef divided by 2 into 2 pi q. Okay, then you are having ef 2 pi raised to power 4 delta, you are having k minus p prime, then you are having mod of a, so what is that, 4 times p dot p prime minus. Okay, so now let's evaluate this thing. समझ आओ? Okay, so I have not assumed any kind. Okay, so this is a direct calculation. I have not assumed whether okay, in which frame we are doing the calculation. समझ आओ? Now in order to evaluate this very integral, we need to choose a frame to simplify this very formula. Huh? Yes, there is a g square. Good. Okay. Okay. So now look at this very delta function. Delta function gives me what? The conservation rule? True? So what kind of conservation is? Huh? Huh? So let me choose frame of reference. Okay, it gives us the obvious moment conservation. Okay, so what I will do, I will assume. Okay, so before doing that, okay, so let me assume. So our boson M is the rest mass of the boson. That boson, and you are having M for rest mass of fermion and antifermion, because they are of the, we will assume this fermion and antifermion pair having what? The same mass. Clear? So for this process to happen, so this I have already told you, M should be actually greater or equal to this 2M. So rest mass should be like this. Or MC square should be greater or equal to twice MC square, because C is equal to 1 in our case. I am using those units. Now what I will do, so to evaluate this kind of formula, what I will assume, so this is the assumption. So I will assume my initial particle is in the rest frame. I mean to say the initial particle decays in its own rest frame of reference. Clear? So that means I am assuming my initial particle to be at rest. Clear? So initial particle, initial boson to be at rest. So what does that mean? So it means the K, okay? So K mu is equal to what? What that is equal to? So that will be only the energy, rest mass, and the momentum is 0. So it will be simply equal to this M 0 0 0. समझ आओ? So it means, okay, so what is actually K mu? So you are having K mu is equal to the initial energy EI, okay, then you are having the momentum, initial momentum. Initial momentum is 0, that's why you have put 0 0, and initial energy is simply rest mass energy. So समझ आओ? Okay. So what about this P mu? So P mu will be simply equal to, let's say the P is the momentum of the electron. Clear? So it will be simply M. Clear? Rest mass energy there. The 3 momentum vector for that very particle. Clear? Let me, instead of M, I should not put M. So it is the rest. It is, let's write it as a EP. Then you are having this P prime mu. That's simply equal to EP prime, okay, and P prime. समझ आओ? Is it clear till this very point? Huh? No, it cannot be M. Huh? Then this P has to be 0. Huh? If this EP is equal to M, because EP is what? What is EP? So it is root of P square plus M square. And what is EP prime? So that's root of P prime square plus M square. समझ आओ? Okay. So now let's go to this very delta function, what it gives us. Delta functions gives us the conservation rule. I want to evaluate this very factor. Okay. Now this delta function, delta 4, so it's actually delta 4, we should do that. Delta 4 K minus P prime, it actually enforces what k is equal to p plus p prime. समझ आओ? So now square the two, so which implies k square is equal to p plus p prime whole square. So what it gives me? So it is simply p square plus p prime square plus twice p dot p prime. Is it clear? Now what is k square? Now tell me what is the square of that k? Its k square is this thing. Sorry, this is k. What will be k square? It will be simply m square. So which implies, so this is m square. Now what is this p square? P square. P square will be actually e square minus p square. So what is that? M square, small m square. Huh? So this is actually m square plus twice p dot p prime. So what it is? So it gives me actually this p dot p prime. Okay. So what it gives me? So it gives me m square minus twice m square divided by. समझ आओ? Got it? Huh? So now let's use it here. So call this as second. Okay? So just give me just 5 minutes. I'm almost done. Huh? So using second. So now if you see, now look here. I am having p dot p prime. It is what? These kinematical variables. This also is a mass. So that means this very factor does not carry any kind of momentum integration. I will take it what? Out of the integrals. So what I will get? So using in equation 2, so I will get this gamma is equal to, so 4 times, so then you are having m square, okay, 4g square divided by twice. What is the initial energy? Tell me. EI is the initial energy, is it? So this is the initial energy, yeah? So it is m. So it is simply m. Then you are having, so let's take this 2 pi raised power 4 out. Okay. Then you are having 4, okay, 4 I have already taken. P dot p is what? So it is something m square half minus m square, clear? Then you are having minus m square. Okay? Then you are having integral, okay, yeah, d f divided by 2 into 2 pi q twice, yeah, okay, delta 4 k minus p minus, okay. So what that is equal to? So now let's take it. So it's minus 12. So it is m square minus 4m square divided by 2. Okay? 2 and 2 is 4, so it's like this kind of thing. So multiplied by g square is 2 pi raised to 4. Okay? And let me write the other integral as rho. So rho is our other integral. So rho is, we call this as the phase space integral. Now tell me, how many momentas are the final momentas? 2 final momentas. So it will be d3p divided by 2 into 2 pi q twice, okay, e p. Then it will be d3p prime divided by 2 into 2 pi q, okay, twice e p prime. I think I should take all these factors out. So it will be there, this delta 4. Okay, this delta 4 I can write, okay, so this object I have put as rho, okay, which I am simplifying as, I can write it as delta 0, k0 minus p0 minus p prime 0, means 0 components, time component, because it's a symbol, it's a 4-dimensional delta function. Okay, so then I am having this delta 3, k vector minus p vector minus p prime. समझ आओ? Usually it is what I mean by that. So if you are having this delta 3 vector, okay, so let's say vector x, so it means actually delta of x, delta of y, delta z. So how many you are having components here? What? So it means that this delta function gives the conservation of energy, and this gives you what? Conservation of 3 momentum. So it's actually both gives simultaneously they happen. So that's why we call it as a conservation of 4 momentum. So समझ आओ? Okay. So let's evaluate this very delta function quickly. So we are done. We are done with our calculation. We need to evaluate this very integral. Clear? Now let's take a look at this very delta function. So we are using which frame of reference? Rest frame of the initial particle. Clear? So where k is equal to this vector k is equal to 0. Okay. So for our calculations, so this is equal to this delta function is simply delta 3 p plus p prime. समझ? Because you can take minus. It is actually minus p prime. Delta function is an even function. You take minus out. Clear? So समझ आओ? So now let's look at what are the variables which depends on p and p prime. So you are having ep and ep prime. They depend only on these p's. This does not depend on what? P. समझ आओ? So now you can integrate over p prime. So let's integrate over p prime. Okay, now look here. So you are having this ep is what? ep prime is root of p prime square plus m square. Let me write. Now when I integrate over p prime, what I will get? P prime is equal to minus p. समझ? So this delta function forces me what? P equal to minus p prime. What does it mean? Suppose you are having particle at rest, it decays. Both the particles move actually in the opposite direction. समझ? So that's what this condition gives me. समझ? Okay, so now let's integrate over p prime. So integrate over p prime. So what you get? So once you integrate, so you should put actually a vector here. Although this also a vector. It is a 3 momentum. Right? So integrate over p prime. When you write p integration over p prime, this p prime will be replaced by minus p. So समझ? That means it will be minus p square. That is same as what? P square. So समझ? So that means I can write it as same as ep square. Got it? So this ep prime will be same as ep prime. So integration over p prime implies ep is same as. So there is no other factor where the p prime exists. So which implies therefore this rho is equal to, take all these factors out. Right? So it is 1 divided by 4, 2 pi raised to 6. Okay. Then you are having 2 to 4. So it's 1 divided by 60. Right? Then you are having integration over d3p prime. Okay. So d3p divided by ep square. Clear? Because ep prime is same as ep. Okay. So there is an integration over p. That's why you have to put this ep within the integral factor. Okay. So then what you are having is delta 0, k0. What is k0? K0 is actually m. Is it? What is this p naught? Huh? It is ep. Good. It's minus ep. So minus ep. Okay, because ep prime is same as what? ep. So समझ आओ? So what you get? So you are having integral. So 1 divided by 16 2 pi raised to 6 integral. Okay. Now let's work it out. This d3p. It will be something 4 pi. Class. Huh? Okay, so let's stop here. Right? So let me do it in the next class. This very critical. Huh? So it is simple 2 steps. Not more than that.